Emotional context during encoding modulates recognition electrophysiological activity. Abstract. The aim of the study was to determine whether experiencing a non emotional event in a positive or negative emotional context affected recognition of the event and the related electrophysiological activity. 28 adults participated in a betting game task in which they could win positive emotional context or lose negative emotional context money. The participants also completed a non betting task, non emotional context. Afterward, the participants completed a no new recognition task for faces with neutral expressions that were encoded during the betting and non betting game. Event related potentials and autonomic responses were recorded. The stimuli learned in the positive emotional context were better recognized than those learned in the non emotional context. The FN400, the parietal new effect, and the late frontal new effect were modulated by positive valence. Learning information under a positive emotional condition enhances its later recognition and the brain activity that underlies this process. Introduction. It has been well established that emotion enhances episodic memory. That is, the ability to remember our own experiences. This type of memory is composed of events and contexts in which they take place, and both events and contexts are better remembered when they are emotional compared to when they are not. Moreover, memory for negative emotional events is superior compared to that for positive emotional events. However, most of the studies of emotional context have observed that non emotional events encoded in positive emotional contexts are more memorable than those encoded in negative emotional contexts, although no differences between positive and negative valences have been reported. The difference in emotional valence effects between events and contexts may be due to the difficulty in controlling for equivalent arousal levels between valences. The arousal levels correspond to the autonomic activation elicited by the emotional valence and can be measured by parameters such as the skin conductance response, SCR, peripheral temperature, or heart rate. Therefore, if positive and negative valences engender different arousal levels, their effects on memory cannot be attributable only to valence. The influence of this possible confounder is enhanced if the emotion is inherent to the event, because when a negative or positive emotion event is represented during recognition, the participant re experiences that emotion. Conversely, the examination of neutral events encoded under emotional context does not engender this emotion re experience. Neurophysiological techniques such as functional magnetic resonance imaging, fMRI, and event related potentials, ERPs, are particularly useful for separate studies of the brain activity that underlies the encoding and recognition of emotional experiences. During encoding, the ERP technique has revealed that the so called subsequent memory effect for non emotional events learned under positive emotional context is enhanced compared to that for those learned under negative emotional contexts. Likewise, neutral stimuli presented in positive emotional contexts that were subsequently recognized generated greater brain activity in parahippocampal and extrastriate visual regions than those embedded within negative emotional contexts, according to an fMRI study. The effects of neutral events encoded under emotional context on recognition neuronal activity have been mainly observed in the prefrontal cortex and amygdala. The activity in the former was more enhanced for correctly remembered events that were encoded in positive emotional contexts relative to those learned in negative contexts. These latter events were associated with major activity in the amygdala. The effects of contextual valence during encoding on recognition physiological activity have rarely been examined. Ventura Borch et al. 2016 compared the old new effects, that is, the amplitude difference between recognition hits and stimuli, correctly identified as new correct rejections, for non emotional objects encoded in pleasant, unpleasant, and non emotional scenes, used as contexts. The authors found that objects learned in emotional contexts were better recognized than objects learned in non emotional contexts. They did not observe significant differences between valences on behavioral performance. However, they found arousal and valence effects on the ERP, the classic parietal old new effect, which is primarily associated with recollection, was modulated by arousal without differences between valences. Conversely, at frontal sites from 300 to 500 milliseconds, only unpleasant contacts elicited the old new effect. This component corresponded to the FN400 old new effect, a component that has been associated with recognition without the need to retrieve contextual information. Thus, it has been conceived as a component that reflects familiarity as opposed to recollection, that entails the retrieval of contextual information. In other ERP studies of emotional contexts, the effects of negative emotional context were compared to those of neutral context for non emotional words and images of common objects. The parietal Oldnew effect and the late frontal Oldnew effect, which is related to monitoring processes, for correctly recognized words were greater for those encoded in negative emotional sentences than for those present in neutral sentences. However, Yeager and Rugg, 2012, failed to find differences in any of these new effects. Smith et al. 2004 attempted to compare the encoding images of common objects presented in negative, positive, and neutral contexts. Although recognition was higher for stimuli encoded in positive contexts compared to those learned in neutral contexts, no electrophysiological differences between valences were observed during recognition. The different outcomes observed in previous ERP studies may be attributable to the type of contexts employed and the relationship between the context and the item. 3 studies employed as stimuli common neutral objects embedded in scenes from the International Affective Picture System, IAPS. In the case of the two first studies, the contexts were completely unrelated to the item. In the Marathas and Rugg 2001 study, the stimuli were words presented within sentences. The close relationship between the item and the context in this study may explain the effects of emotional context on the old new effects, which were absent in the other studies. Similarly, the emotional modulation on the old new effects observed in the Ventura Board et al. 2016 study could be attributable to the fact that their participants were instructed to indicate whether they were capable of imagining a relationship between an image and a scene. This is a good approach to join both elements, but the participants had to make an effort to achieve this relationship, and it was not generated in an automatic way. The present research builds on these previous studies by employing a paradigm that ensures a natural association between the item and its context to examine the effects of encoding stimuli under emotional and non emotional contexts on recognition responses, both behavioral and neurophysiological. Effects of the valence of the context on recognition have been observed in fMRI studies. However, in ERP experiments, whether the valence of the context will have an effect remains an open question because valence effects were absent in the only previous study that evaluated these effects. Therefore, in the present study, we compare the effects of positive and negative emotional contexts on the old new effects. Moreover, we included an SCR measure during encoding to ensure that the arousal levels elicited by the two emotional valences were equivalent to control for this potential confounder variable. To address these questions, we designed a paradigm in which participants were engaged in a gambling task with a virtual opponent that was represented by a photograph of a face. The participants could lose or win money, negative and positive contexts, respectively, in each trial. Additionally, the participants completed the same task without gambling to examine recognition for stimuli presented in non emotional contexts. Afterward, the participants engaged in the old new paradigm for the faces of the virtual opponent. The encoding phase of the current study has already been published, and we found that faces encoded in positive contexts were better recognized than those encoded in non emotional contexts, consistent with other studies. Therefore, we expect that during recognition, the neurophysiological responses for stimuli encoded in positive contexts will be of greater amplitude than the responses for those encoded in non emotional contexts. In particular, we predict that the parietal and frontal new effects will be present for faces encoded in both positive and negative contexts. The latter part of this hypothesis is based on the findings of Maratos and Rugg, 2001, and Ventura Bosch et al., 2016. However, these effects would be of greater amplitude for faces encoded in positive context because recognition is enhanced in these conditions. Because the stimuli used in the present study were faces, we also expected that the N170, a component related to facial processing for faces encoded in positive contexts, would be of greater amplitude than those encoded in negative emotional contexts. This prediction is based on a previous study that observed that faces encoded with positive emotional expressions relative to those with negative emotional expressions elicited a greater amplitude N170 during retrieval when the faces had neutral expressions. Methods: participants. 28 right handed adults participated in the study, half were men. The original sample consisted of 30 adults, however, two of them were excluded due to excessive artifacts in the ERP data. They were 25.4 with a standard deviation of 3.9 years old and had 16.9 with a standard deviation of 3.1 years of formal education. The participants were not addicted to drugs or alcohol and reported the lack of the use of central nervous system altering medication. All had normal or corrected to normal visual acuity and did not suffer from psychiatric or neurological disorders. None were gamblers or fans of gambling games. The participants provided informed consent, and all procedures were approved by the Ethics Committee of the School of Medicine of the National Autonomous University of Mexico. Stimuli. The stimuli included 540 color photograph faces with neutral expressions. The faces were of unknown Occidental people between 20 and 80 years old. Half were of females. The photographs were digitally edited to avoid the presence of accessories or clothing. 60% of the portraits were obtained from 3 different standardized databases. The remainder was photographed for this study. 20 independent judges indicated whether the faces had neutral expressions, and only faces classified as neutral by all judges were included in the study. The images were projected onto a white background and were framed by a black square. The faces had horizontal and vertical visual angles of 2.5 and 3.5 degrees, respectively. The total pool of stimuli was randomly assigned to 18 blocks of 30 stimuli each. From each block, 15 stimuli were selected at random for the encoding phase, in which the participants completed the betting game, and the total set of 30 stimuli was presented in random order during the recognition phase. The emotional context was based on the result of the betting game, winning or losing. The probability of winning in 6 blocks positive emotional context and losing in 6 blocks negative emotional context was controlled by an algorithm that was devised to set such probabilities to p equals zero point 0.7. The remaining six blocks corresponded to the non emotional condition in which there was no betting. The blocks were presented randomly, although three blocks from the same condition were prevented from appearing consecutively. Paradigm. The encoding phase consisted of playing a betting game, which either the participants of the or the virtual opponent could win. The winner of the trial was the one who reached a total sum closest to 10 without exceeding this number. Each trial began with the appearance of a black fixation circle that was displayed for 200 milliseconds. Afterward, a blank screen was displayed for 200 milliseconds to serve as a baseline. Then, a face was displayed for 1000 milliseconds during this period, and the following 1500 milliseconds, in which a blank screen was presented, the participants had to indicate whether the face was attractive or not. Immediately after, a square divided into four sections was displayed for 2000 milliseconds. Two numbers from 0 to 9 were displayed in the left column. The number in the superior row was assigned to the participant, and the one in the inferior row was assigned to the virtual opponent. The participant and the virtual opponent decided whether they wanted another number or not. If they were required, the numbers were then displayed in the right column for 2000 milliseconds. If they were not required, a hyphen was depicted. The number or hyphen of the winner was displayed in green, while that for the loser was depicted in red. The participants won or lost 10 Mexican pesos each trial, approximately zero point 0.6 US dollars. The screen remained blank for the following 200 milliseconds as a baseline period, and then the face of the virtual opponent reappeared for 1000 milliseconds. The participants were then asked to indicate whether they had won or lost the trial. The screen remained empty for the following 1500 milliseconds, and the participants were able to provide their response after the appearance of the face and during this period. Immediately, a green circle was displayed for 1000 milliseconds to indicate that blinking was allowed. At the end of the trial, the amount of cumulative money won or lost in the block was displayed for 300 milliseconds. In the non emotional condition, the procedure was equivalent to that for the emotional context, except that hyphens were displayed instead of numbers for the virtual opponent. Therefore, the participants could not win or lose. In this condition, the callers for the second numbers or hyphen were randomly assigned, and participants had to indicate the color of their number or hyphen when the face of the virtual opponent was displayed for the second time. At the end of the trial, instead of the amount accumulated, two X's were displayed. The recognition phase took place after each encoding phase. Each trial consisted of the presentation of a black circle, a baseline period, a face photograph, and a green circle. The timing of these events was the same as was used during the encoding phase. The participants performed an old new task in which they had to indicate whether the faces had been previously presented during encoding, old or not, new. For both phases, two panels containing a single button were used to provide all responses. The buttons assigned to the different options for each response were counterbalanced across participants. Procedure. The participants completed two sessions. In the first, they were interviewed to assess whether they fulfilled the inclusion and exclusion criteria. Then, they performed brief versions of the encoding and recognition phases as practice. At the end of this session, the participants were informed that the maximum amount of money that they could lose or win was 300 Mexican pesos, approximately 16 US dollars. Thus, the participants were rewarded with 100 Mexican pesos, approximately 5 US dollars, and to complete the maximum 300 Mexican pesos they could lose, they were asked to bring 200 Mexican pesos, approximately 11 US dollars, to the second session. In the second session, the participants performed the task while their electrophysiological activity was recorded in a sound dampened, dimly lit chamber. They were seated in a high backed armchair 100 centimeters away from the monitor screen. Additionally, we recorded the SCR. At the end of this session, the participants completed a questionnaire that included pictorial faces to assess how they felt when they won and lost, as well as during the non betting task. The participants who lost were reimbursed the money they lost when the experimental session ended. Note that none of the participants knew in advance that they would be reimbursed in the case of losing. Electrophysiological recordings. Electrophysiological recordings and autonomic responses were obtained using a brain vision quick amp acquisition system with 126 AGAGCL electrodes. The recording was monopolar, and we used the average from all electrodes as a reference. The data were re referenced offline to TP9 and TP10 electrodes that correspond to mastoids. The electrooculogram EOG was obtained by placing an electrode in the outer canthus of both eyes to measure horizontal eye movements, and another electrode above and below the left eye to measure vertical movements. All electrodes had an impedance of less than 10 kilo ohms. Both the EEG and EOG were continuously digitized at a rate of 500 Hz with a bandwidth between zero point 0.1 and 100 Hz. The signal was digitally filtered offline at 20 Hz using a zero phase shift low pass filter. The SCR was recorded by an electrode placed on an intermediate phalanx of the annular and medium fingers. Electrode paste was applied to the electrodes to facilitate the signal conduction. These electrodes delivered a constant voltage of zero point 0.5 microvolts. The left and right hands were counterbalanced across participants for the SCR recordings. During the encoding, the SCR was measured from the onset of the second number because at this moment, the participant knew the result of the bet. Epochs of 4,700 milliseconds were created for these measurements until the offset of the green circle. Data analysis. The electrophysiological activity during recognition was first corrected using a Grayton et al. 1983 algorithm to eliminate artifacts to eye movement. Then epochs of 1100 milliseconds, including a 200 millisecond pre-stimulus baseline, were created. The epochs for recognition hits were averaged separately according to the context in which they were presented during encoding, positive, negative, or non-emotional context. The data for new correctly identified faces, correct rejections, were also averaged. The number of epochs was equivalent across all conditions. The data from 3 electrodes were averaged at 3 regions of interest, frontal, parietal, and occipital, and at 3 sites, left, center, and right. The frontal and parietal electrode leads were selected to measure the frontal and parietal new effects, and the occipital ones were chosen to measure the N170, which is associated with face processing. The mean amplitude was measured in 3 latency windows: 140 to 200 milliseconds, 200 to 500 milliseconds, and 500 to 1100 milliseconds. The first one was set to analyze the N170, while the second and third were set to examine the parietal and frontal all new effects, respectively. The latency windows were chosen based on previous studies. Data from each latency window were submitted to separate repeated measure ANOVAs with the following factors: trial type, position, and side. Scalp topography analysis were conducted on the data recorded with all electrodes. These data were first normalized using the max-min method proposed by McCarthy and Wood. The data were first rescaled to avoid finding effects due to differences in the magnitude instead of differences in the sources. Then normalized data for hits in each context were subtracted from the correct rejection. Repeated measures ANOVA analysis were conducted for the differences of each latency window. These analyses included the factors of electrode site 126 and context, positive context, negative context, and non-emotional context. For the SCR, the mean amplitude for each epoch was calculated and normalized using the previously reported method. A baseline of 20 seconds was recorded for each participant before the beginning of the task. During this baseline, the minimum skin conductance level, SCL, was measured. The lichen and venables method consists of subtracting the minimum SCL from the mean SCR amplitude of each epoch and dividing this result by the difference between the maximum and the minimum SCL. The maximum SCL corresponded to the highest value obtained during the entire experiment for each participant. Normalized data were submitted to repeated measures ANOVA that included a factor trial type. Latency to peak was also calculated. Additionally, Pearson correlation analyses were performed to test whether the recognition hits were related to the SCR or to the ERP amplitudes, and whether the SCR were related to the ERP amplitudes at each emotional context. Tukey's honest significant difference, HSD, tests were computed as post hoc analysis. The degrees of freedom were corrected using Greenhouse-Geiser method. The original degrees of freedom, the Greenhouse-Geiser coefficient, and the corrected probability levels are reported. The significance level was P less than 0.05. All analyses were performed based on performance in each trial without considering the type of block in which the trial took place. Results: behavioral data. Performance during the encoding test did not significantly differ between contexts for any of the responses required or for the reaction times. For a complete report of these analyses, see Martinez, Galindo, and Cancino 2015. The repeated measures ANOVA of recognition hits revealed a significant effect of context, positive, negative, and non-emotional. The post hoc analysis indicated that recognition for faces encoded in the positive context was higher than that for those encoded in the non-emotional. However, recognition for faces encoded in the negative context did not differ from that for those encoded in the other two contexts. The mean percentage of correct rejections, false alarms, and misses was 85.9 with a standard deviation of 9.2, 13 with a standard deviation of 8.1, and 25.3 with a standard deviation of 10.3, respectively. Reaction times were analyzed through a repeated measures ANOVA that included a factor context. This analysis was not significant. Mean reaction time for correct rejections, false alarms, and misses was 698, 934, and 826, respectively. Trials in which the participants failed to encode the stimulus or did not provide the answers during recognition were excluded from all analysis. An additional repeated measures ANOVA was performed to test whether the attractiveness of the faces influenced recognition memory. The analysis included the factors of attractiveness, attractive or unattractive, and context, positive, negative, and non-emotional. Neither the main effects for the attractiveness factor nor its interaction with the context factor reached significance. The repeated measures ANOVA conducted on the data obtained from the questionnaire applied at the end of the session, which included the factors context and clip art, revealed a significant interaction. The results are depicted in Table 1. Post hoc analysis revealed that there were no differences between the maximum of the emotion experienced during winning and the maximum of the emotion experienced during losing, although these two clip art faces differed significantly from all of the other ones. Autonomic responses. The one-way ANOVA computed on the SCR data recorded during encoding revealed a significant effect of context. Post hoc analysis revealed that the amplitude for subsequent hits for both emotional context, positive and negative, differed from that for subsequent hits from the non-emotional context. But there were no differences between hits for the positive and negative contexts. Additionally, we performed analysis of the area under the curve and of the latency peaks, and we confirmed that there were no differences between valences. A complete report of these analyses is included in Martinez, Galindo, and Cancino 2015. The correlation analysis conducted for each latency window between recognition hits and ERP amplitudes in the three different contexts were not significant. The correlation between SCR and ERP amplitudes performed at each latency window for the three contexts were also not significant. Conversely, Recognition hits in a positive context were significantly correlated with SCR, but not with the other two contexts. ERP data. Only results involving the factor trial type are reported. The factor trial type was significant in the second and third latency windows, but not in the first latency window. The post hoc analysis revealed that the amplitude for the hits encoded in the positive context was greater and more positive than that for those encoded in the other trial types. The amplitude waveforms did not significantly differ among the other trial types: negative context, non emotional context, and correct rejections. The interaction between the trial type and the position were significant for data recorded in the second and third latency windows. In the second latency window, the post hoc analysis for this interaction showed that there were significant differences between the trial types at only the frontal sites. The hits for faces encoded in the positive context elicited a more positive waveform than the hits for faces encoded in the negative context. The hits for faces encoded in the non emotional context and the correct rejections. There were no significant amplitude differences between the last three trial types. In the third latency window, post hoc analysis revealed that at the frontal sites, the hits for faces encoded in the positive context elicited a more positive amplitude than that for those encoded for all the other trial types. The amplitude from positive context also differed from the amplitude of the other trial types at parietal and occipital leads. The amplitude waveforms that did not significantly differ among the negative context, the non-emotional context, and the correct rejections. In any latency window, the interaction that included the factor side were significant. Topographic analysis. The results of the ANOVAs conducted on the scalp topography data were significant for the interaction between context and electrode site in three latency windows. However, post hoc analysis revealed that there were no significant differences between trial types for any of the electrode sites. Discussion. Behavioral results. The positive context enhanced memory for neutral events. This outcome is in agreement with results from other neurophysiological studies that have examined the effects of emotional context on memory. Moreover, the advantage of positive context on recognition hits was observed under conditions in which the arousal level of both positive and negative contexts was equivalent, as revealed by results from SCR and the emotion experienced by the participants, which was reported through the questionnaire. Therefore, the differences in memory performance observed are reliable and only due to valence. This outcome is confirmed by the significant correlation between SCR and the recognition performance that was observed for only the positive contexts. The positive emotion experienced by participants correlated with their ability to recognize faces. However, the experience of negative emotion was not related to their memory performance. The lack of reaction time differences across recognition hits for faces encoded in the different emotional and non-emotional contexts indicate that context had no effect on the speed of processing related to the identification of old faces consistent with previous studies. Electrophysiological results. The emotion experienced during the encoding of faces influenced the electrophysiological activity recorded during the recognition of the faces. However, this activity was modulated not by emotion in general, but by valence, given that only the hits encoded in a positive context elicited the frontal and parietal new effects. These electrophysiological outcomes follow the same pattern that was observed for the behavioral data. In the following, we discuss how positive emotion modulated the different components analyzed. The earliest component measured was the N170. This is a well-known component associated with facial feature processing, especially emotional expression. Moreover, the N170 has been frequently recorded in face recognition studies. It has been observed that at encoding, the N170 is enhanced when information is learned in a positive emotional context. However, contrary to our expectations, this component was not modulated by arousal or valence in the recognition phase. Therefore, positive emotion enhances facial analysis at learning. But when the face must be recognized, emotion influences the later mechanisms of memory as opposed to the initial facial processing. The second latency window was measured to analyze the frontal and parietal new effects. The electrical activity recorded at frontal sites was highly influenced by the emotion that the participants experienced during encoding, as revealed by the finding that old new effects were manifested before those of the parietal sites. However, different processes underlie these effects. The earliest component modulated by valence was the FN400, an old new effect that has been related to familiarity. The FN400 was not found to be modulated by emotional context in two previous studies of immediate memory, but it was modulated by negative emotional valence in a study of emotional context that tested memory 1 week after the encoding phase. Outcomes from this study and the present one confirm that familiarity is influenced by valence when there is a close relation between the item and the context. Positive emotion enhanced immediate memory, and negative emotion influenced long lasting memory. The other frontal component modulated by positive valence was the late frontal old new effect. This component has been related to post retrieval processes. That is, its amplitude is believed to reflect brain processes that occur after a recognition decision has been made, such as monitoring or evaluating the accuracy of the response. In the current study, the mean reaction time for hits was 767 milliseconds, and this waveform was recorded between 500 and 1100 milliseconds, confirming that a memory decision was made before the late frontal effect reached its highest amplitude. Neutral words encoded in negative context have also elicited the late frontal new effect. Therefore, the present findings reveal that this component is not exclusive to negative contexts. However, if the positive emotional contexts are just as arousing as the negative ones, then the positive valence is the one that enhances the process of monitoring. In the Moratos and Ruggs study, only negative valence was examined. Therefore, it remains unknown whether their study, the effect of positive valence on the late frontal effect, could have been greater than that of negative valence as observed in the current study. The parietal new effect has consistently been associated with retrieval processes that involve the recovery of specific information present when the event was first experienced. Recognition tasks do not allow the differentiation of recollection and familiarity. However, the valence mediated modulation of the parietal new effect indicates that recollection might have occurred in the present study and that this process was greater for positive compared to negative emotional contexts. In fact, it was exclusive to the positive valence, given that hits for faces encoded in the negative context did not show this new effect. One previous study found that a negative emotional context modulated the parietal new effect in a recognition task, but not in a retrieval task. The authors of this study concluded that emotion affects the parietal new effect when its influence is incidental, as occurs in a recognition task, but not when the emotion experienced during encoding has to be explicitly retrieved. The parietal new effect was observed until the end of the epoch, both in the Moratos and Ruggs study and in the present one. Taken together, the findings from both studies revealed that the parietal new effect is sensitive to emotional valence. The three new effects analyzed were modulated by positive valence. However, the topographic distribution of these effects did not depend on valence, suggesting that the sources of the electrical activity recorded from the scalp were equivalent for both valences. In addition to the classical new effects, a slow wave recorded at occipital sites was modulated by emotional valence. This effect has not been previously reported in recognition studies that have used emotional contexts. However, in a continuous recognition task for emotional items, an new effect was recorded at similar latencies and sites. Conversely, in this study, This effect was modulated by high arousal items and not by emotional valence. Venstrian et al. 2009 probably observed this arousal effect because the emotional items elicited a re experience of emotion during recognition. In contrast, in our study, emotion was not explicitly present at recognition. Therefore, arousal might have masked a potential valence effect, as observed in the current study. The occipital slow wave observed in the current study probably reflected restatement processes, that is, the reactivation of perceptual mechanisms that were present at encoding. The so called cortical reinstatement hypothesis has been supported by several ERPs and fMRI studies. Conclusion. In summary, the present data suggests that when we learn non emotional information under positive emotional circumstances, we are more likely to remember that information in the future than if it was encoded under negative emotional contexts. In addition, we were able to distinguish which ERP components were influenced by positive emotional valence. The encoding of non emotional faces under positive emotional conditions enhanced the memory process via familiarity based recognition, FN400, non explicit emotional valence recollection, parietal old new effect, and recognition judgment monitoring, late frontal old new effect, and probably the reinstatement of the original encoded episode, occipital slow wave.